In previous generations, the base stations were controlled by a central device. In 2G, it was the base station controller, and in 3G, it was the RNC. These controllers were responsible for setting up the radio links to wireless devices via the base stations, for controlling the connections while in use, for ensuring quality of service, and for handing over a connection to another base station when required. In LTE, this concept was abundant, as it required significant resources because the task was concentrated in few network nodes. Most applications on the device only transmit and receive information in bursts with long timeouts in between. During these times of inactivity, the air interface connection to the mobile devices has to be changed to use the available bandwidth efficiently and to reduce the power consumption of mobile devices. So, the packet switch connection generates a lot of signaling load because of the frequent switching of the air interface state. So, these management tasks were distributed to speed up the connection setup time and reduce the time required for handover, which is very crucial for real-time services, thus making the LTE access network a simple flat network of interconnected base stations without a centralized controller. Hello everyone, welcome back to the world of LTE. Today we will discuss the radio access network of LTE, which is also called Evolved eUMTS Terrestrial Radio Access Network or eUTRAN. The most complex node in the LTE network is the base station, referred to as eNode B. It is derived from the name which was originally given to the eUMTS base station Node B, with an E referring to evolve. eNode Bs consist of two major elements. RRU, or the remote radio unit, consists of the antennas. It is also called remote radio head, which are the most visible parts of mobile network. They are also responsible for modulation and demodulation of all signals transmitted or received on the air interface. The second part is BBU or baseband unit, which consists of digital modules that process all signals transmitted and received on the air interface and acts as an interface to the core network over a high-speed backhaul connection. Now, in LTE, base stations are autonomous units. Most functions of the RNC were integrated into the eNode B. Hence, the eNode B is not only responsible for the air interface but also for radio resource management that includes radio bearer control, radio admission control, connection mobility control, and scheduling, that is, dynamic allocation of resources to UEs in both uplink and downlink. It is also responsible for IP header compression and encryption of user data stream, selection of an MME at UE attachment when no routing to an MME can be determined from the information provided by the UE, routing of user plane data to a service gateway, scheduling and transmission of paging messages originating from the MME, scheduling and transmission of broadcast information originated from the MME or ONM, measurement and reporting configuration for mobility and scheduling. Now, the interface between the base station and the core network is referred to as the S1 interface. It is usually carried either over a high-speed copper or fiber cable or alternatively over a high-speed microwave link. The S1 interface is split into two logical parts, which are both transported over the same physical connection. User data is transported over the S1 user plane part of the interface. IP packets of a user are tunneled through an IP link in a manner similar to the already described for GPRS to enable seamless handover between different LTE base stations and eUMTS or GPRSH. In fact, the GPRS tunneling protocol GTP is reused for this purpose. Only the destination IP address on layer 3 is changed, while the user's IP address remains the same. The S1 control plane protocol, as defined in 3GPP, is required for two purposes. Firstly, the eNode B uses it to interact with the core network for its own purposes, that is, to make itself known to the network, to send status and connection keep alive information, and for receiving configuration information from the core network. Secondly, the S1CP interface is used for transferring signaling messages that concern the users of the system. For example, when a device wants to communicate using the LTE network, an individual logical connection has to be established, and the core network is responsible for authentication, for supplying keys for encrypting data on the air interface, and for establishment of a tunnel for the user's data between the eNode B and the core network. Once the user's data tunnel is in place, the S1CP protocol is used to maintain the connection to organize a handover of the connection to another LTE, eUMTS or GSM base station as required. In S1CP protocol stack, instead of the commonly known TCP and UDP on layer 4, the telecom-specific Stream Control Transmission Protocol (SCTP) is used as defined in RFC 4960. It ensures that a large number of independent signaling connections can be established simultaneously with in-sequence transport, congestion management, and flow control. Now, as mentioned earlier, unlike the previous generation technologies, LTE integrates the radio controller function into the eNode beam. This allows tight interaction between the different protocol layers of the radio access network, thus reducing latency and improving efficiency. Such distributed control eliminates the need for a high availability, processing-intensive controller, which in turn has the potential to reduce cost and avoid single point of failure. One consequence of the lack of a centralized controller node is that as the UE moves, the network must transfer all information related to a UE, that is, the UE context, together with any buffered data from one eNode B to another. So, to avoid data loss during handover, X2 interface was introduced. In LTE, base stations can communicate directly with each other over the X2 interface for two purposes. First, handovers are now controlled by the base stations themselves. If the target cell is known and reachable over the X2 interface, the cells communicate directly with each other. Otherwise, the S1 interface and a core network are employed to perform the handover. The second use of the X2 interface is for interference coordination. As in eUMTS, neighboring LTE base stations use the same carrier frequency. There are areas in the network where mobile devices can receive the signals of several base stations. If the signals of two or more base stations have similar strength, the signal of the base stations that the mobile device does not communicate with at that moment are perceived as noise, and the resulting throughput suffers significantly. As mobile devices can report the noise level at their current location and the perceived source to their serving base station, the X2 interface can then be used by the base station to contact the neighbor base station and agree on methods to mitigate or reduce the problem. So friends, in this video we have seen how limitations of previous generation were mitigated by decentralizing the radio access network in LTE. In our next video, we will be discussing about the evolved packet core. Happy learning!